You are welcome to FANOC Research Group YouTube channel. Please click on the subscribe button to subscribe to our YouTube channel. You will get notified whenever new video is uploaded. Thank you.
Sequences of real valued functions. Sequences of real valued functions. Real valued functions. Okay. So that's exactly what we want to look at today. I'm sure you recall we looked at before now, we've looked at sequences of real numbers. In other words, you have a sequence of real number, which is a function that has a domain. The domain is actually a subset of n, Domain is a subset of n, if you like, is in n, and the range is in R. That's talking about the real sequences, which we looked at. It's a function that has domain in that. We've seen a lot of such. For example, 1 over n. We have 1 over 3n. Of course, n, the entire natural number system. We have even had the alternating sequence of this type. So all of those, we've seen that. But we've already considered convergence of things, of sequences of this nature, convergence, divergence. We've also seen series. So, but now, this chapter, you'll be talking of, instead of sequences, you'll be talking of functions. That's the major difference. These are functions of real numbers. You know that this sequence can converge. For instance, you can say that this xn, if, for example, xn is 1 over n, this sequence converges to number 0, number 0 in R as n goes to infinity. But here, you will not be talking of sequences, you'll be talking of functions. So functions will converge to another function, not just a number, not just a number, unlike sequences of real number that will converge to numbers, or maybe you have something like this one, 1 over n plus 1. This also goes to 0 as n goes to infinity. Okay, so these are sequences. And then this one, if you list it, it's not convergent. You have minus 1, 1, minus 1. This is the famous oscillatory sequence. Okay, though bounded below by minus 1, bounded above by 1. We've done a lot of analysis on this. So, but today we will be looking at functions, sequences of function. In other words, you have function now as a sequence, n counting from 1 to infinity. In other words, if you are listing the elements, the first element of this sequence will be function f1, f2. They are all functions, f3, and so on and so forth. So if you are now talking of this function converging to f, okay, there are two possibilities. Number one, f could converge to f pointwise, okay, or f could converge to f uniformly. We are going to look at all those possibilities, all those concepts rather. So, I just needed to recast or recall some of the things we've done so that we can see the relationship between what we did in R, sequences in R, and also now that we want to look at sequences of real numbers. So let me share another slide so that we can begin the business immediately. Okay. So the first thing we need to do is to, first of all, define what we mean by a sequence converging, okay? Converging to a sequence of function converging pointwise and also uniform. We need to define that. So let me call this definition. Definition. I'm coming. Okay. So I have definition. Definition Okay? Let Fn a sequence of functions. Let Fn be a sequence of real value function, real valued functions. Of course, you can write out explicitly what you mean by that. That's you have Fn. The domain of your F is actually a subset of R, just like every other function. Of course, the range is also in R. This function is defined on D. Domain of is D. So defined on a subset D of the, of course, the subset is D of R. Just a subset of R. Then, if that is the case, then the sequence which we call Fn is said to converge. This sequence is said to converge pointwise. I said there are two possibilities, pointwise and uniform. So let's begin with the first one. Pointwise on D, which is the domain of the function, of course, to F. You can see the limit of Fn of the function is another F. So you discover that just like all the concepts we studied about functions, like continuity, like, all those things, we can study about the limit of a function, because the limit of a function is yet another function, not just a number, which has also its domain and range. So to F, okay, that F is another function. So, and every function will have its own domain. Of course, the domain will still be in R, of course, in another. So you discover that the limit of a function, when a function converges to F, that limit also is a function, and it has its domain and its range. Okay, so it's said to converge pointwise to F if and only if and only if for every epsilon greater than 0, and of course a given a particular given x. This one is not uniform. This is a fixed x. In D, you can always find a natural number, call it capital N. Of course, that natural number will depend on both the epsilon and the x. That's why it's pointwise. X is relevant. So it will depend on both the epsilon as well as the x. Okay? Of course, that natural is a natural number. So it's a natural number in the natural number system. Okay? Such that you have that the modulus of Fn at the point you are talking about, which is x, minus the limit of Fn. Fn is the sequence of function. So, but f is what you claim to be the limit. Applied at that x, that fixed x, are the we picked before, which is this particular the modulus of this is less than epsilon, and that will happen for all n greater than the n you are talking about, which is this one. Okay, so you now discover that pointwise continuity will depend on two things, the epsilon and x. When we come to uniform continuity, you discover that x is irrelevant. That's the major difference between pointwise and uniform convergence. We'll come to that later. But for pointwise convergence, x is relevant. The point, because you are saying that this can happen only on x, on a particular x. On a particular x. It will not happen maybe for another x, maybe for another y in D. Okay, this may not hold. This inequality may not hold for another point, maybe y in D. It may not hold. It may just, the inequality may be reversed. So that's why you discover that this n will depend on both epsilon and x, and that's a pointwise convergence. I will share the geometrical aspect of that definition with us, just like I did when we were studying when we are studying studying sequences, I also try to give you geometrical interpretation of that. So let me do the same thing for here. This uh, okay. Of course, you know that here we are talking of functions. You're not talking in real numbers in sequence of real number. We looked at x, the real line. Okay, where you can say that xn converges to x. What you simply mean is that every open interval opened on the what you call x star. Okay, the limit. We contain all the terms of that means for every epsilon greater than 0, you can always find a particular n, okay, which will depend on epsilon and x. Okay, this n is, call it n, such that for all n greater than that n, you have that all the terms of the sequence will lie in between here. Okay, but here that's for real numbers. But for functions, you are talking of the way you can plot it. You can talk of the x and y axis. Okay, such that you are claiming that this function converges to f. Okay, to f. Let's say this is your f. This is your f. You now discover that here, what it's saying is that for every epsilon greater than 0, your f of x, which is plotted at this, every other function will always lie within this strip. We always be lying within this strip. Okay, you always be plotting them very close to the f. In fact, as n goes to infinity, all of them will converge to f. Okay, to the f. So every other number as n, for example, fn plus 1, fn plus 2, okay, fn plus 2, fn plus 3, and in fact, fn plus 4, and in fact, as n goes to infinity, all of them, all those functions, you can plot them. You can plot the graph very close to f. That's the geometrical interpretation of what we mean by pointwise convergence. Okay, so just like here when we were dealing, I need to, I normally put side by side so that you can, draw inference or see how we migrated from the chapter we dealt with sequences of real numbers to now that we are looking at functions. You recall that when we are here, when we are in real number, we looked at sequences like this one over n, as n goes to infinity. We said that this n sequence converges to 0. Geometrically, what it means is that if 0 is my x star now, any open interval, because in R, open balls are open intervals. So any open interval with epsilon distance, of course, a ball must have radius. The radius is epsilon, okay? Because epsilon is greater than 0. So epsilon is any epsilon neighborhood of 0. We contain all the terms of this sequence as n goes to infinity, okay? All of them will be here. As n goes to infinity, like 1 over 1 million, very close to 0. 1 over 1 trillion, very close to 0. As far as n goes to infinity, all of them are piling up at 0. So 0 is the limit as n goes to 0. So that's any open interval centered on 0. We contain all the terms of the sequence as n approaches infinity. The only ones that will be outside will be finite. You can say maybe, oh, it's just the first 3 terms, x1, x2, x3. It must be finite. The ones outside this ball, no matter how small your epsilon is, okay, that's what we mean. The same thing here, but here we'll be talking of strips because you are drawing diagrams of functions. Okay, so that's just side by side of what we mean by pointwise convergence on R, and now that we're talking about a pointwise convergence of functions now. Okay, so let me produce some examples. Possibly we'll make more meaning from those examples. Let me produce some examples now. And then we'll proceed from there. Okay, so nice one now. So we we talk about examples. Examples. Okay, look at this example. If you have a particular n in n, define define your sequence, which you can represent as fn between this domain D now is just 0, 1, and the range is also 0, 1. All these are subset of R. So as simple as that. You define this function, this sequence by the following. Define it by saying fn at x is simply x to power n. Okay, and this will happen for every x in the domain of f, which is 0, 1, close bounded. Okay, if you define this by this, you now make the following observation. For instance, if x is 0, for each n, if x is 0 if x is 0, that means 0 to power n for all n. What do you observe? 0 to power n will be 0 now. So for if x is 0 for all n, it then means that fn at 0 is what? 0. Because if you replace x 0, 0 to power n, it's always 0 for whatever value of n. So it's 0 for all n. That's the first observation. And another observation is that you discover that if x is 1, okay, that means you have fn at 1. What would that be also? It will be 1 as well. And that will happen for all n. You know, if you replace this x to be 1, 1 to power n, for, just 1 to power n. N are natural numbers. For example, 1 to power 1 is 1. 1 to power 2, 1 squared is 1. 1 to power 3 is 1. So 1 to power 100 is 1. So 1 to power n is 1. So for all n. Okay, so we make the following claim. Okay, number one is that, number one claim we are making is that fn at 0 converges to 0 as n goes to infinity. That's number one. Number two is that fn at 1 converges to 1 as n goes to infinity. And lastly, we deal with the open intervals now. So fn at x will converge to 0. I continue here. As x is lying between 0, 1. See the interval. This interval does not include the endpoints. It's an open interval, so it doesn't include 0, it doesn't include 1. 0 and 1 have been settled by claim 1 and 2. So you are now looking at the interior of this. So that's 0, 1, excluding the endpoint 0 and 1. So within this range, for every x in 0, 1, and also as n goes to infinity, you have that fn at x will go to 0. Okay, so where we can justify those claims, let's prove those claims. I'm sure you have to look at them so that as we go ahead, we are going to prove one. One says that if you have this function, this is a function, and then we are to show that fn at 0 is 0 as n goes to infinity. And not only that, fn at 1 is 1 as n goes to infinity. And the fn at x will be 0 when you are in the interior of this 0, 1 set. So excluding the endpoint, that's the interior. The largest open set of any set is interior, that's the interior of the set. So that's 0, 1. So we can go to the next slide so we can justify our claim 1, 2, 3. Okay. So let me share yet another new slide so we can proceed. Okay. Now, the claim 1, of course, I'm sure you recall claim 1. Claim 1, claim 1 you have to show that Fn at 0 converges to 0 as n goes to infinity. First of all, if this is the case, what do you mean by that? So if you allow epsilon, any epsilon greater than 0, be given, okay? And of course, x is 0, x is 0. So, and x is 0. Well, then what that simply means is that the modulus Fn at 0 minus f at 0 is 0. So 0. Of course, f at 0, Fn at 0, we've already, is 0. So this is equal to 0. And of course, this is less than epsilon. Okay? And this will happen. In fact, this will happen for any n greater than or equal to 1. Okay? So actually we can choose, for convergence, once you can compute your n, your job is done. So you can actually choose your n, because here, for any n greater than, of course, we know the natural number system counts from 1, 2, 3, and 4. It works for all n. So for any n, for instance, you have your n to be depending on epsilon, and of course, epsilon and x. Our x in this case is 0. So for that n, any n that you pick, beginning from 1 and above, will do the job. So your ability to have computed your n does the job. So what have you shown? You have just shown that the sequence of function, which is Fn, converges to f, okay? Of course, where f is 0, f of x is 0, is a 0 function, not 0 number. I'm sure you know that. Where actually your f of x is not the 0 number, it's a 0 function. It's the 0 function. Okay, and that will happen for every x in the entire domain D of f, which is 0, 1, close bounded. Okay, so we have established claim number 1, which says that this function converges to 0 as n goes to infinity. So we've been able to compute our n. That's always the job. Just like when we are in continuity, you must compute the delta, okay? But if you are not able to compute the delta, then that function is not continuous. I'm sure you recall that. The same thing happened on convergence. Convergence, you must produce n such that for all n greater than that n, the convergence you are talking about will happen. And for this particular case, is the entire natural number system, which is 1, 2, 3, 4, and so on and so forth. So, meaning that the function, this inequality is not violated. Look at the inequality, not violated. 0 is less than epsilon. Of course, that's the definition. So, that's claim 1 is justified now. So we go to claim 2. I share the next slide to proceed with that one. Share the next slide. Claim 2, let me recall claim 2 so that we know what exactly we are doing. Claim 2 says, what did claim 2 say? It says Fn at 1 will converge to 1 as n goes to infinity. Okay, if you recall, that's claim 2. Well, if that is the case, we need to prove that as well. If that is the case, we choose any epsilon greater than 0. Of course, this a given epsilon. Okay, and of course, our x in this case is 1. So our s is 1, and x is 1. Okay, if that is the case, then we have the following. Let's put it in the inequality. Then the inequality, the modulus of Fn at x, but x is 1 in this case, minus f at 1. We've already shown that f at 1 is 1. Remember how our function is defined. Fn at x is equal to x to power n. So f at 1 1 to power any number is 1. We've already established that at the beginning. So that's at 1. F at 1 is 1. So, and of course, if you look at it, F at 1 is 1. So this will be like 1 minus 1, which is 0. And of course, this 0 is less than epsilon. Okay? So once again, this happens for all n. Okay? This will happen for any n greater than or equal to 1. So actually, you can choose, you can actually choose your n as follows. You can choose your n. Your n, of course, will depend on the epsilon of your choice, as well as your x. But your x in this particular case is 1. Okay, just choose 1. Okay, 1. Any n for all n, all n greater than or equal to 1. It follows that fn at x, fn modulus of fn at 1 minus 1 is less than epsilon. Okay, that justifies the claim, so that you now discover that fn at 1 converges to 1, which is our claim number 1. So as n, of course, as n approaches infinity. Okay, so that's pointwise convergence. This function converges pointwise to 1 as n approaches infinity. So that's verification for 1, claim number 1. Okay, so claim number 3 has to do with interior. The domain is now the interior of 0, 1 closed bounded. So we're going to lose the outer boundaries. And let's see claim number 3 verification as well. Claim number 3, I record that so that we can see what we have. Claim number 3, we claimed in number 3 that, what was that now? That fn at x, okay, we converge to 0 for all x now in 0, 1. This is the interior of, remember our domain was 0, 1. Martin, what is the difference between this set and this set? Are they the same? Because for this, your case 3, this is the domain. For all the other cases, this is the domain. Case 1 to 2 is this domain. So the domain, what are they the same? That's my question. Martin, Ruben, anybody can answer that. I need us to.
It's not the same. It's not the same. Yeah.
It's not the same.
Yeah.
What's the relationship between this set and this set? What's the relationship?
Maybe they have the same supremum and infimum point, but the first one is
the subset and superset. Yeah, I want that done there.
Yeah, the open bracket is a subset of the closed one.
Good. 0, 1 actually is a proper subset
Proper
of
subset
0.
of
Yeah.
Yes.
So that's the thing. So I'm sure we've not lost sight of that. So let's justify this first of all. Let's justify this. What do you mean by this? Well, what you actually mean is that for any epsilon, you also let epsilon be greater than 0. This given, okay, and of course my x is between 0, 1. Okay. Now you will do the following observation. Observe, actually, for every x in that order. Observe that x in 0, 1 implies that the modulus of x is less than 1. Is that correct? Is that correct? Any number in between from here to here, the modulus of x is less than 1. That's the absolute value of that number is less than 1.
Yes,
because
sir,
1 is not. So this automatically guarantees, okay, if you find the reciprocal of both sides, This guarantees that 1 all over modulus of x, okay, is, when you find the reciprocal, you reverse the inequality. So this is greater than 1. Okay, this is greater than 1. Okay. Now, of course, we will not have issues with this. We won't have issues with this because we have already avoided 0. The domain, there's no 0. If 0 is here, we would have had issues. So but there's no issues with that. So since x is different from 0, we don't have issues actually with that domain. So we can let, for instance, we can have 1 over modulus of x to be equal to, actually 1 over modulus of x, will be 1 plus something, a positive number actually. 1 plus, I don't know, but let's call it a px, depending on the x, the positive addition will depend on the x you choose. So let me call it 1 plus a positive number. Okay, this expression is greater than 1. Okay, so let's call it 1 plus a number which will depend on the x you pick. Okay, and this will happen for some px, and that px, of course, is greater than 0. That we are very sure of. So if that is the case, you now have that. Don't forget the way f is expressed. The sequence is expressed as what? As x to power n. So if that's the case, this like your x now. So you now have that you now have that 1 all over modular, of course, 1 to power n is n. So the only one that will be affected is the denominator. So you have x modulus n. Okay, of course, by binomial expression, you can work out this as 1 plus, we've already said that this is 1 plus a number px to power n. Of course, by binomial expansion, this is greater than 1 plus npx. Okay, okay. And of course, this 1 plus npx is obviously greater than nps. Of course, nps is greater than npx. Of course, it's greater than by 1, obviously. And this will happen for all n in the entire natural number system, which is n, the entire natural number system. So what's the meaning of this? The meaning of this is that I want to share another slide so that we continue. The meaning of this is that you discover that this number is positive, obviously. This number is positive. So in other words, this 0 is less than or equal to npx, okay, modulus x to power n, okay, and of course this number is strictly less than 1, and this will happen for every integer n in the entire natural numbers. Of course, we've already avoided 0, so it does make sense. Okay, from the domain of f, 0 is avoided. Okay, so with this, we can begin to estimate our n. I'm sure you know that that's our goal, to estimate our n in which the initial inequality will hold. So let's see what we have now. Okay. So you see that 0 is less than or equal to x to power n. Okay, this less than 1 over npx. Okay, and this for the entire natural number system, and s avoiding 0. Okay, so this inequality holds for, of course, this inequality will still hold for x to be 0. Even if x is 0, you can still do this. So hence, you discover that it holds for all x such that you have that the modulus of x is less than 1. Okay, so if that is the case, you can now go back to your original inequality, which says that fn at x, okay, minus 0, okay, what would that be? Of course, you only be interested in this, but fn at x is exactly the modulus of x to power n. We've already said that this is less than 1 over npx. And of course, this obviously is positive. This is less than epsilon. Okay? So you now see that you can begin to, from here now, you can begin to make n the subject. You can begin to make n the subject, because that's your job. That's exactly where you're going to. So you now discover that if n, from here now, from this side now, if you make n the subject, if n is greater than 1 all over 1 all over p x epsilon, then you can now actually find that for any given epsilon greater than 0, as well as x in 0, 1 open, you have that the following. You have that the modulus of fn at x minus 0 is less than epsilon. So what's the meaning of this? This simply means that fn converges to the sequence, that is, the sequence fn converges to f pointwise. Okay? Of course, the function is defined to f. That's talking about the limit now. The limit f of x is defined as 1 if x is 1. Let me share a new slide to you. But of course, we've already seen all that. But it will be 0 when you have x lying between 0 and 1, excluding 1. Okay? So that's the establishment of those justification. And as I said, all of these geometrically, they are functions. So they are functions, and we can actually construct them or draw them. So let's proceed by showing some of the, we can construct some of the diagram. I've already drawn that before now. But let me just demonstrate that once again. Of course, in two-dimensional space, you have sorry, you're not all that straight, so, but I'm sure you know what I'm saying. This is your x-axis, okay? This like your F1, F2, and F3. So let's, may not all that be perfect. So this like your, sorry. This like your 1, 1. I'm sure you know the function have 1, 1 on the y-axis, while you have 1, 0 here. Okay, 1, 0 at this point. Okay, so this is your F1, F2, F3. So you discover that this strip, as n goes to infinity, F1, F2, all of them will be piling up close to the limit, okay, of the sequence. So that's not far away from the real line on where the limit x star, any epsilon neighborhood of x star, will contain all the terms of the sequence as n goes to infinity. So, but in R2, you talk about strips. So all the sequences of functions will be contained in the strip, no matter how small the epsilon is, no matter how small. Okay? So we proceed to another example. Maybe we'll give one more example and then we ask some questions. Okay? look at this example. Let me call it example 2. Example 2. Okay. Example. For n, in n, the natural number system, define your sequence of function as follows. Define fn. Define fn. This time around, my domain will be -1, 1, and the range is 0, 1, 0, 1. So we are defining this function as follows. Fn at x, we have 3 values. The first value is 0, and that's for the x values lying between -1 to 0. You can see the domain from -1 to 0, and then 0 to 1 over n, and then 1 over n to 1 at the end. So that's how we partition the domain of f. So between 0 and between -1 and 0, the value of f will be 0. That's -1, between -1 and 0. And then the next value of the function will be nx. Nx, that will be between 0 and 1 over n. And 1 over n. And the last value will be 1. 1 between 1 over n and 1. The last extreme end is 1. So that will be between 1 over n. X will be between 1 over n and the last extreme end, 1. So that's the way that function is defined. That's the way that function is defined. Okay, so we make the following observation. I want to share yet another new slide so we can make the following observation. Now, if you recall, when we are in real numbers, when you have a sequence, sometimes you can easily guess what the limit is going to. But for example, if you have 1 over n, you can easily get, of course, if you write when n is 1, n is greater than or equal to 1, that's the domain of this sequence. You can actually say when n is 1, you have 1, 1 over 2, 1 over 3, 1 over 4. It's easier to guess that this sequence converges to 0 as n goes to infinity. Okay, because you see that as n increases, this tends towards 0. Okay, so many times sequences in R you can actually guess. Okay, but it's difficult to guess that as n goes to infinity, the sequence of fn, the one we defined before, converges to a particular n. It's difficult to guess. Okay, look at this. Let me record that function. Let me record the function. We have fn, that's the sequence, if you recall it. You have 0, nx, as well as 1. Those are the values. And this will happen between -1 and 0. And this will happen between 0 and 1 over n. And this will happen between 1 over n and 1. Okay, so you now see here that guess may not, for instance, if you have the following guess, f of x to be 0 between minus 1 and 0, and as well as 1 between 0 and 1. Now, you can actually sketch the functions if you want. You can actually sketch them, all these functions. You can sketch them on the diagram geometrically. But formally, you can write the following. Please just give me some few minutes, 1 or 2 minutes. Let me put on my power system. Okay. So we are back now. So we can, as I said, we can actually sketch all of those, but we can do the following. Also, formally, we can have that minus 1 is less than or equal to x. Minus 1 less than or equal to x, less than or equal to 0. If that is the case, you have that fn at x as defined is 0. Okay, is 0 for all n greater than or equal to 1. So what's the meaning of that? The implication is that fn at x converges to 0 as n goes to infinity. Okay, now, but within this domain, you have the following. Within that domain, which is 0 less than x less than or equal to 1, you have that there exists a particular, call it nx, which of course is a natural number, such that you have that 1 over n is less than or equal to x, and this will happen for all n greater than or equal to that natural number, nx. So what's the meaning of that? This automatically means that fn at x will be 1, okay? And that will happen for all n greater than or equal to that particular nx. So automatically fn at s converges to 1 as n goes to infinity. So in either case, you discover that the sequence of function as defined converges pointwise to the function f, which we have already defined, function f, which is defined. So that's one of that example. There are several examples that I'm sure maybe when the tutorial comes up, you look as many other examples as possible. Okay?
Hello, Prof. Hello, Prof.
Yes. Yes.
I don't get when.
Yeah.
How can we take fn of x is equal to 1?
How can we get what?
Fn of x is equal to 1, the third line.
You mean this one? You mean this
The above,
one?
the above one. Yeah,
This one?
yeah.
That's already, if you go back to we've already established, we're only making inference to what we have already known. Let me go back to the next slide. We think we've already established all of this, even from definition. Let me see. This slide 10. Okay. Let me share this. Okay. Yeah, in between here and here, this one, when 1/nx is between here and here. So that's what already that has been defined. We are just tapping into the definition. So in between this point, you have the Fn is 1. And we've also, I think, constructed F, if you recall. Let me go back to where you took your question, which is here. So you can see that we are simply repeating what have already been said. So yes, nothing new actually. But all
Okay.
that we just did to actually verify that you can actually get a particular end that this will happen. Okay, so that's the conclusion. I don't know if you've understood that.
I understand. Yeah. Thank you.
It's okay. So let's impose some questions. I'm sure you recall when we studied integration, that's Riemann integration. We looked at limits, and if a sequence converges to f, does it mean that the integration of fn also converges to the integration of f? We asked such questions during that time. So we will now that we are under this topic, pointwise convergence and uniform convergence, we also pose similar questions. So let's pose them. Though I may give you some of them as assignment to solve, so that we can now proceed to the next topic, which has to do with uniform convergence. Okay, so but let's just pose the question to at least to arouse our curiosity, and we see how the answers can go. Questions? Maybe we call this question number 1. Question number 1. Question number 1. If, for example, your sequence Fn is continuous, I'm sure you recall when we say that a function is continuous. Okay, it's continuous because it's a sequence. So you can express this as F1, F2, F3, and so on and so forth. Okay, so it doesn't terminate. So when you are saying continuity, is at all the all the domain, not just the domain, all the all the terms of the functions. In other words, continuous at f1, f2 continuous, f3 continuous, fn continuous, up to f infinity. So that's what we mean by continuous. So continuous for all n. That's exactly what we mean. So it's continuous. Fn is continuous for each n. For each n. The question we want to find out is, does it also automatically guarantee, is f necessarily continuous as well. That's the limit of a continuous function. Is it also continuous? Okay. For example, if you have that Fn converge pointwise to F pointwise. Okay. Does it necessarily mean that Fn continuous implies that the limit is also continuous? Well, just like we did in integrability, there are some conditions that will happen, which we saw eventually, that must be fulfilled for such to happen. Some of them may not happen, some may happen under certain conditions. So maybe after posing the question, I'll just give an assignment. You show us, just like we did with Riemann integral, to give us the condition under which we happen, these questions will happen. Question number 2 is, if you have the sequence Fn, if it's integrable, when I say integrable, Riemann integrable, so you already know what that means. If it's integrable for each n, for all n, okay? Does it necessarily mean is f, the limit of Fn, is f necessarily integrable? Okay. You look at that question also. Number 3, if Fn is differentiable, for each n, and f is also differentiable, does Fn prime converge to F prime? Both F and Fn are differentiable. Does it now automatically guarantee that Fn prime, I'm thinking Fn prime, the differential of Fn, does it converge to F prime? Okay. So what we are simply saying in that question is, does Fn converge to F? Does it guarantee that Fn prime converge to Fn prime, F prime? Okay, that's the question. So that's what this question 3 is talking about. Okay, so there are some other questions like that. Let me just leave it at 1, 2, 3. So you come up, the assignment is you come up with the answers. So question 1 to 3. Okay, so that should be all for pointwise convergence. The next type of convergence is uniform convergence. Okay, so let's proceed now to uniform convergence. Uniform convergence. Uniform convergence. Okay, definition, of course, that's the first thing. Definition. Let Fn, that's a sequence, be a sequence of real-valued real-valued functions defined on a subset D of R, then the sequence, which we call Fn, is said to converge uniformly, is said to converge uniformly on D if given epsilon greater than 0. You can always compute a particular n. That n will depend only on epsilon. You can see here in uniform convergence, x is immaterial. X does not bother us because it's going to happen for all x. So there's no particular x that will disturb us or that the n will depend on. So n will only depend on the epsilon, which of course is a natural number system, such that this inequality, the modulus of Fn at x, any x at all, minus f of x is less than epsilon. As a matter of fact, this will happen for all x, for all. I'm sure you know this symbol means for all x in this. So there's no any x that will be a problem. And also for all n greater than or equal to the n you talked about. So for all n greater than or equal to n. So the main difference between uniform convergence and pointwise convergence, what did I say is it? Somebody should tell us what I said is the main difference between pointwise convergence and uniform convergence. Yeah, I need contribution. What's the main difference between pointwise convergence and uniform convergence?
Hello. In uniform convergence, we are going to check for every x now in the given domain. And also the absolute Fn of x minus f of x.
Okay. So in uniform convergence, x, your n does not depend on x. Your n does not depend on x. Okay. But in pointwise convergence, n depend on both x and epsilon. Okay. That's okay. So let's have the following definition also. We want to talk about Cauchy. I'm sure you remember when a sequence is called Cauchy. So let's talk about uniformly Cauchy functions. Definition. A sequence of function, of course, which is Fn of real valued functions, functions is called uniformly Cauchy. And a set D provided that for any given epsilon greater than 0, you can always find a particular n. That n will only depend on the epsilon of your choice. and of course is part of the natural number system, such that the following inequality will hold. And what's the inequality? The modulus of your sequence at x minus sequence at, these are succeeding terms. Both m and n are greater than this n, so they are just like succeeding terms of f of x will be less than epsilon. This will happen for every x in the domain of the sequence, which is d, and it will also happen for every nm. This nm will be greater than this your choice of n. So this nm will be greater than or equal to n epsilon. Hope that this uniform convergence. So it depends only on n epsilon. So a sequence of real numbers of real valued functions is called uniformly Cauchy if this inequality holds. Okay. So that will lead us to one of the popular theories in analysis, which we call the uniform Cauchy criterion. So uniform Cauchy criterion. We state that theory. That theory many a times is applied in proving a convergence of sequence of functions. Okay, so but let's look at the hypothesis of the theory. Okay, so I call it theorem. And I said this theorem is popularly called uniform Cauchy criterion. Okay. Now, what's the statement? It says if you have, of course, you have a sequence, let Fn, okay, be a sequence of functions, real valued function, real valued functions defined on a domain. Of course, functions are defined on the domain, defined on a subset called the domain D. Of course, the domain is that of a subset of the real number. Then there exists a function called that function f such that the sequence, which is Fn, converges uniformly to F, on D. This will happen if and only if the following condition is satisfied. And what is the condition? That is, given epsilon greater than 0, there exists a particular n which will depend only on the epsilon. Of course, it's also part of the natural number system, such that I'm sure you know this denotation or symbol for such that this inequality will hold. The absolute value of f of n at x minus f of m, these are succeeding terms greater than, all of them are greater than or equal to the n. So is less than epsilon. This will happen for all x in D, for all x in the domain of the function D, and also for all nm greater than your n. Of course, your n is already defined as depending only on epsilon, this one. Okay? So that is that popular Cauchy criterion, uniform Cauchy criterion theory. Okay, so we are going to construct the proof. And of course, the proof, if you look at it, it's not something that will be difficult. The proof will be divided into two. You assume all of this. That's assume that f is a real value function such that fn converges uniformly to f on d. Then you show this. You show that this inequality holds. And then conversely, you prove that if this inequality holds, then fn converges uniformly to f on d. That's just the proof. Okay. So let's try to construct the proof. Let's construct the proof. So as I said, the theory is divided into two, the necessity part and the sufficiency part. So let's begin with the necessity part. The necessity part, okay, the necessity part, meaning that you assume that suppose that f converges to fn, f is such that's fn. You know, the first part is that fn converges to f. So suppose that f is such that fn actually converge, that's the sequence converge to f uniformly. I'm sure you know, that's the hypothesis. If you go to the first part of the hypothesis, fn converges to f uniformly converges. I'm sure you remember what that means. What does that mean? To say that fn converges to f uniformly. What it simply means is that for epsilon greater than 0, you can actually find a particular n, which of course will depend on the natural number, which will depend on epsilon, and of course it's part of the natural number system. You can always find an n such that the following inequality will hold. Fn converges to f. So Fn minus f is less than epsilon. Of course, this f, you can also put x there. So it's, for generality's sake, Fn of x minus f of x is less than, I can say epsilon over 2. Why? Because the criteria for epsilon is that the division for epsilon is greater than 0. And if a number is greater than 0 and I divide it by 2, it's still greater than 0. So I have not violated anything. And this will happen for every x in the domain of D, domain of f, which is D. And this will happen for all n greater than this n, for all n greater than equal to this n, which you have already picked. Okay. Also, if you get, apart from this n, if you get another number m, okay, greater than this will also be satisfied. In other words, if you say let that m be greater than or equal to n, or even if that n is another number after m, it will still happen, because that's convergence. That's what convergence means, uniformly. Every n after this one, this inequality will not be violated. So if I pick m, for example, is greater than equal, then this inequality will also hold. Then I have that the modulus of fm at x minus f at x will also be less than epsilon over 2. Okay, and this will happen for all x in D. And of course, this will happen for every m this time around greater than or equal to this n. Okay, any number, natural number greater than this n, this inequality will hold. That's the meaning of uniform convergence. And obviously, you can combine, if you like. If you call this equation 1, you can combine 1 and 2. You can combine 1 and 2. You combine 1 and 2, you have the following. We have the following. If you combine 1 and 2, you now discover that for epsilon greater than 0, you have that for epsilon greater than 0, you can actually find Because remember, your n epsilon is part of the natural number, such that you can find n such that the modulus of remember we are in real valued function, so triangle inequality will be satisfied. That's one of the properties of real numbers. So fnx minus fmx, okay, by triangle inequality, of course I can say that this is equal to, if you like, I can say that this is equal to fn of x minus f of x plus f of x. So I've not done anything. Then minus fm of x. Okay? I've not done anything. I only added minus plus. I've not done anything. So, of course, these are real numbers. Okay? Triangle inequality will be obeyed. So the whole of this will be less than or equal to a modulus of fnx minus fx, fnx minus fx plus this side fx minus, which is fmx minus fx. Okay, we already know this candidate, we already know this one. This one, by the last slide, this is the limit of this sequence. This sequence converges to this, so this is less than epsilon over 2, is it not? Plus this side also, if you recall, that's equation 2 on the other side. This sequence converges to this, so this is less than epsilon over 2. Epsilon over 2 plus epsilon over 2 is what? Epsilon. What have you done? You have just shown that established the last part of that theory, which says that the modulus of fn of x minus fm of x is less than epsilon for all n greater than or equal to n epsilon. Is it not? This is the last part. If you go back to the last part of that theory, so you see that we assume that fn converges uniformly to f, and we've arrived at this conclusion, which is the last inequality for that uniform convergence criteria. If you go back to that last slide, I'm sure. Let me go back and show you what I was saying. Look at this. So look at that. This is, so we assumed fn converges uniformly to f, and we've arrived at it. This is where we've arrived. fnx minus fmx is less than this. So you see, that's where we've arrived. So that proved the necessity part. Now, to prove the converse, that's the sufficiency part. We assume this and then prove that fn converges uniformly to f. Okay, fm converges uniformly to f. So that's the next part of the proof. Okay. Okay, so let's go back. Let's go back and then to prove the next part. Okay. So we want to prove the sufficiency part. Okay. And that sufficiency part, you have that the following. Suppose that the uniform Cauchy criterion is satisfied. What's that uniform Cauchy criterion? Somebody should tell me, what is it? That is what? The modulus of fn minus fm at x, right, is less than epsilon for all epsilon greater than 0, for all nm greater than a particular n, which depends on epsilon. Okay? Is it not? So that suppose this is what we have. This is the uniform Cauchy criterion. Okay? Now, what's the meaning of this? This means that Fn, the meaning is that Fn, the sequence, is a Cauchy sequence. Is Cauchy in R. Okay? Is Cauchy in R. And of course, there's one thing we know about R. We've already established in R. R is a complete space. Okay? So, by completeness of R, what does it mean? By completeness of R, the meaning is that if a space is complete, every limit of the sequence will be in that space. We cannot fall outside the space. So by completeness of R, it implies that it automatically guarantees that Fn okay, converges and the limit is also in R. That's sure. That's a well-known result. Okay, so we can actually, since it converges and so we can define the following. We can actually say that f of x, okay, is equal to the limit. Of course, if it converges, it means that if you take limit as n approaches infinity of fn at x, it will be f. We can do the same, and this will happen for all x in D, and of course for all n for all n greater than that n. The n here depends only on epsilon. Okay? Now, we now need to show. So, sure, certainly, yes, it converges. Our job only to complete this scheme is to show that this convergence is uniform. Because the only thing we have here is convergence. We don't know whether it's pointwise. But the theory gave us, our job in the theory is to show uniform convergence. But certainly it's convergence. So the next thing is to show that the convergence actually is uniform. If you can do that, then the job is done. Okay? So we proceed as follows. We proceed as follows. Of course, we claim that this convergence is uniform. Okay? We claim, which we must also establish, claim that convergence is uniform. Okay? Is uniform. Because if that is the case, we have the following. For epsilon greater than 0, of course, you have that there exists a particular n which will depend only on epsilon. Of course, this n is part of the natural number system. Why? Because you've already had the Cauchy criterion axiom, okay, such that for all nm greater than or equal to n, by Cauchy criterion, you have that the modulus of fn at x minus fm at x is less than epsilon over 2. This will happen for all x in D. And if you fix n and you let m go to infinity, then you have that fm at s will converge to f of x. And this will happen as m go to infinity. Okay? The same thing if you fix m, you will also have that the modulus of fn at x minus f of x is also less than epsilon over 2. So if you combine the two results, you see that it automatically follows that Fn converges uniformly to F. So that's the proof of that result. Okay, so we show some more examples and then we proceed. I'm sure this class we should be rounding up uniform convergence also, so that by next class we now look at some special series of functions, and then we now conclude reanalysis. Okay. I want to find out from you the tutorials you have been having. Where are you now? Ruben, have you been attending? And Martin, where in particular are you now in your tutorials?
Yes, sir. We
Particular
have
topic.
covered some parts in limitation and limit of definition of like a right-handed sorry
Okay.
right-handed limit and left-handed. Yes, that part was our session on Saturday. It's Sundays.
It's okay. So that's basically around limits and continuity. Okay. I'm sure with time you'll catch up with problems in this area. Okay, so we are far ahead of the tutorial. I'm sure the tutorial will come up and then also complete the course very soon. Okay, so let's pick up maybe just one example and then we are done with this and then we proceed with the next section. Okay, so let me just give the following example. If you have n part of the natural number system, if you define your sequence of function, if you define your sequence of function, the domain of your sequence, just as simple as 0, 1, 0, 1, and the domain is R. If you define that by the following, Fn at x is equal to x all over 3 plus nx. Of course, this x, the domain is the domain of f, which is 0, 1. Okay, and of course, this will happen for every n in the entire natural number system, which is 1, 2, 3, and so on and so forth. So our job here is to show that this sequence Fn converges uniformly, okay, on 0, 1. Okay, well, this problem will be solved using that last theory. You remember what we said? If this sequence must converge uniformly to this, then the Cauchy criterion theory must be satisfied, is it not? So that meaning that we can use that theory to solve this. If we check and the Cauchy criterion is satisfied, then it then means that the assumption that this converges uniformly to this uniformly on this is correct. So, but if the Cauchy criterion, that theory we just proved now, if it's not satisfied, then we just say that that claim is wrong. So proof, we must show that the Cauchy uniform, or the uniform Cauchy, that the uniform Cauchy criterion is satisfied. Is satisfied. So that's what we must do. Okay. Who can state that uniform Cauchy criterion here? Can you remember? Giving epsilon greater than 0, right? You discover you can actually find there exists a particular n which will depend on epsilon, call it n, okay, such that the modulus of fn at x minus f minus fm at x will be less than epsilon, and this will happen for all n m greater than the n. This is exactly the Cauchy criterion. So we'll be verifying whether this is satisfied vis-a-vis this problem. Okay, so if this satisfied, then we conclude that yes, this conclusion is correct. But if it's not satisfied, we also said no, it's not. It doesn't follow. Okay, so that's the job. We're just simply applying that theory to solve this problem. And that's what you do in mathematics as you are learning. Your analysis, as you do your research, you may have some sequences of functions to contend with. So you can apply the Cauchy criterion the way we apply it to solve this problem in resolving your own problem. So, solution. I'm sure you remember the problem we are solving. Solution. Let's your m be greater than n, convergence. Let m be greater than n. And of course, m and n are part of the natural number system. Of course, you also choose any epsilon greater than 0. Those are, and then you choose your n, which you are always looking for. This n will always depend on epsilon. And of course, it's part of the natural number system. Okay? You choose this such that your n is greater than, for example, 2 over epsilon. It's also positive. And if that is the case, you have that for all n greater than n, this one, for all n greater than n, you have the following, that the modulus of fn at x minus fm at x. I'm sure you remember how this is defined. Do you recall? Let me remember, flip back. Your function is defined as follows, as x all over 3 plus nx. 3 plus nx. This will happen for all x in 0, 1. Okay, and for all n greater than or equal to 1. So don't lose sight of how your function is defined. Okay, don't lose sight of that. So this, obviously, if you do the difference, you'll be having equal to x all over 3 plus, for this one, nx, okay, minus what? X all over what? 3 plus mx. Okay. Of course, you can put this and this together. You can put this and this together. If you do that, you have x squared into m minus n all over 3 plus nx also into 3 plus mx. Okay. Of course, these are, what these are. So these are real numbers. So this is less than or equal to, and you already know where your x is taken from. X is taken from 0, 1. So this whole inequality is less than or equal to this, which is modulus of m minus n all over mn. All over mn. Okay? Of course, you can break up this. To be less than or equal to modulus of, you can even remove the modulus. You have 1 over n plus 1 over m plus 1 over m. Okay? So the job is almost done. You already know that this candidate, we've already said that your n, your capital N is greater than 2 over epsilon. So 2 over epsilon. So with that, you can begin to compute your n as follows. So you now discover that the whole of that last inequality is less than 2 over n, and 2 over n, of course, 2 over n is less than 2 over capital N, because n is greater than this. Okay, n is greater than this, so this is less than 2 over n, and of course this, from the argument we had, is less than this. And then what's all that we have concluded? Now by Cauchy, you discover you can now apply now by Cauchy criterion, uniform criterion. You have that that sequence Fn converges uniformly to F on 0, 1. Okay? So that's the application of that theory to that to solving that problem. Okay? So we state some other theorems as well. We state some other theorems that are also are highly applicable in analysis. Let me call here theorem. Let Fn a sequence. Let Fn be a sequence of real valued functions In fact, not just real valued, the real valued continuous function. Let me share another slide so that I will state that theory in another slide. It will be better that way. Then we now make our explanation there. Okay. Theorem. Let Fn, a sequence of functions, be a sequence of real valued continuous functions on a set D in R if you have that sequence Fn converges to F uniformly on D, then F is continuous, on D. That's already answering some of the questions we posed before. If Fn is a sequence of continuous functions on a set D in R, if Fn converges to F uniformly on D, then F is continuous on D. So that I've already answered, I think, question 1, if you recall. So that's telling you that the condition needed for uniform convergence of Fn to F, meaning that F, is continuity. Continuity is what is needed, really. Okay, and the proof, you can actually do the proof. It's not all that difficult. You follow the methods of proof we've already adopted for the last one. Let me give you yet another theory. Okay. Theorem. Let Fn be a sequence of real valued integrable functions, real valued integrable functions on AB close bounded, and I'm sure you know that's the domain that Riemann integrability can hold. So let the sequence Fn converges to F uniformly, okay? Converges to F uniformly on AB close bounded, okay? Then F is integrable, Riemann integrable, so you must know that. Integrable on AB, okay? And as a matter of fact, you can do the following. If you take the limit as n approaches infinity of this integral, of course, you're integrating from AB close bounded, of Fn at x, you integrate with respect to x. This will amount to the integral from A to B of just the limit of the function, Of course, you do this integration with respect to x. So this also answering one of the questions that was posed before now. I was posed before now. Okay. So I'm going to give you some exercises for you to work on. Okay, I think the one I gave to you, I've already solved many of them. So let me better give you an exercise which you will submit. So let me share a new slide and then write it down. Then you can copy and then solve it, and then you send it by email to me. You already have my email. So assignment now. Assignments. For each integer, n greater than or equal to 1, let your sequence be defined as follows. Fn, let Fn of x, of course, Fn of x be equal to 5, number 5, over 5 plus x to power n. This sequence is defined on 0, 1, 0, 1, close bounded. Question A, prove that this sequence Fn converges pointwise pointwise on the domain of F, which is 0,1, close bounded. And the second question, B, is asking, is the convergence uniform? Is it a uniform convergence? Of course, the hint, if it's a uniform convergence, then the Cauchy criterion must be satisfied. I'm just giving you the hint for B now. But is the convergence uniform? Whatever is your answer, you have to justify it. Justify your answer. Okay. So that's the assignment for you to look at.